Walk into a modern heavy-duty dealership today, and it looks more like a surgical theater than a mechanic shop. The floors are polished epoxy, wide enough to eat off of. The air smells like lavender cleaner instead of diesel and gear oil. There isn't a drop of fluid on the ground. You see technicians standing around in clean uniforms, holding tablets, looking at bar graphs on a screen. They trust that screen more than they trust their own eyes. They believe that if the software says the machine is healthy, then the machine is healthy. But if you walk past the pristine diagnostic bays to the back corner, where the lighting isn't quite as good, you will find the truth. There sits a 2024 model year heavy hauler. It has 50,000 miles on the odometer. That is barely the break-in period for a commercial diesel. It should be running 20 hours a day, hauling freight across the interstate. Instead, it is sitting here, cold and silent. The engine is seized solid. The crankshaft will not turn. The technician assigned to this bay is confused. He has plugged in his diagnostic tool, and the tablet is telling him that all systems are green. The fuel pressure reads normal. The oil pressure history shows no drops. The sensor array, which cost more than my first house, reports that this truck is in perfect working order. But the metal tells a different story. The metal is dead. While the young guys are scrolling through pages of code looking for a software update or a sensor calibration error, I am looking for something else. I am looking for a physical flaw that hasn't been seen in this industry for 35 years. They see a random catastrophic failure. I see a birth defect. This engine didn't die because of bad luck. It died because the factory that built it forgot its own history. They stopped reading the blueprints from 1988, and now the iron is paying the price. If you want to see the scale of this problem, you have to leave the air-conditioned shop and walk out to the back lot. We call this the hospital ward, but honestly, it is more like a graveyard. There are 6 trucks lined up against the fence. Every single one of them is a 2024 model. Every single one of them failed between 48,000 and 52,000 miles. They are gathering dust, waiting on back-ordered engines that might not arrive for 3 months. This creates a crisis for the fleet owners. These people operate on razor-thin margins. A truck that isn't moving is a truck that is losing money. When they call the dealership, they get the standard corporate line: "We are waiting on parts." But the dealership isn't trying to fix the engine. They are waiting to replace it. We have entered the era of the parts changer. The modern dealership model is not built on diagnosis. It is built on replacement. When an engine seizes like this, the warranty protocol doesn't pay the technician to tear it down and find the root cause. That takes time, and it requires skill. Instead, the manufacturer pays a flat rate to swap the entire assembly. They pull out a $20,000 engine, crate it up, and ship it back to a refurbishment center where it will be melted down or stripped. Then they drop a brand new crate engine into the truck and send it back out on the road. They treat the symptom, but they ignore the disease. This is what we call a ghost defect. A ghost defect is a failure mode that exists entirely in the physical world, completely outside the view of the electronic control unit. The ECU monitors voltage, pressure, and temperature. It does not monitor the fatigue strength of a casting or the harmonic vibration of a tensioner arm. If a bolt shears off because the metal was too porous, the computer doesn't know until the engine stops turning. There is no check engine light for bad metallurgy. The tragedy is that the fleet owners are often blamed for this. I have heard service managers tell customers that their drivers must be abusing the equipment. They accuse them of over-revving the engine, missing oil changes, or idling too long. They say, the computer shows no faults, so it must be operator error. It is a convenient lie. It shifts the liability away from the manufacturer and onto the customer. But these trucks were not abused. They were maintained by the book. I checked the logs myself. The oil was changed every 15,000 miles. The filters were premium. The drivers were veterans with perfect safety records. These trucks were treated like gold, and they still died on schedule. The failure is happening in the diagnostic bay. The standard procedure is to plug in the scanner, read the codes, and follow the flowchart. If the flowchart leads to a dead end, the technician throws up his hands and orders a new engine. They have stopped asking why. They have accepted that machines just break sometimes. But machines don't just break. Physics is consistent. If 6 engines fail at the exact same mileage in the exact same way, there is a reason. It is written in the metal. But you have to be willing to get your hands dirty to read it. You have to stop looking at the digital twin and start looking at the iron reality. To understand why this happens, you have to understand how a modern truck thinks. We treat the electronic control unit, the ECU, like it is an omniscient brain. We assume that if something is wrong with the machine, the computer will know about it. But the computer does not know the machine. The computer only knows what its sensors tell it, and those sensors are wearing blindfolds. The problem lies in the difference between analog reality and digital interpretation. An engine is an analog device. It operates in a world of infinite variables: vibration, heat, friction, fluid dynamics. But the computer is digital. It takes snapshots of that reality. It doesn't see the whole movie, it sees a slideshow. This is a matter of sampling rates. A standard sensor on a 2024 heavy-duty engine might report its status to the ECU 10 times a second, or maybe 50 times a second if it is a critical system. That sounds fast, but in the world of mechanical rotation, it is an eternity. When an engine is spinning at 1,800 RPM, the crankshaft is rotating 30 times every second. If a vibration is happening at a high frequency, say 200 times a second, the sensor literally cannot see it. The vibration happens in the gaps between the data points. It gets worse. The engineers who program these computers know that engines are noisy places. There is always some vibration, some fluctuation in pressure. If the check engine light came on every time a sensor saw a momentary spike, the truck would never leave the yard. So, they program the software to smooth out the data. They use algorithms to average the readings over time. They tell the computer to ignore the noise and focus on the trend. That is the fatal flaw. In this specific case, the noise isn't noise. It is the sound of the engine dying. The computer is programmed to ignore the exact frequency that is killing the machine. Take the oil pressure, for example. On the screen, the graph is a flat, steady green line. It says 55 psi, perfectly within spec. But that is an average. If you hooked up an old-school mechanical gauge with a needle, you would see that needle vibrating like a guitar string. You would see the pressure spiking and dropping violently with every rotation. The digital sensor sees the average of 55. The mechanical gauge sees the reality. The oil film is being hammered into non-existence. The technician looks at the screen, sees the green line, and stops looking. He says, "Oil pressure is good." He is wrong. The oil pressure is a lie. This brings us to the culprit, the automatic belt tensioner. On the surface, this is a simple part. It is just a spring-loaded arm that keeps the accessory belt tight. It runs the alternator, the water pump, the AC compressor. It doesn't seem like a critical internal component. But on these modern engines, the tensioner is mounted directly to the front of the engine block, right next to the crankshaft pulley. When this tensioner fails in a specific way, it doesn't just stop working. It starts to chatter. It sets up a harmonic vibration that travels through the bracket, into the block, and straight into the nose of the crankshaft. It acts like a jackhammer. It isn't a massive blow. It is a microscopic tap, 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 occurring thousands of times per minute. The ECU has no sensor on the belt tensioner. It has no way to feel that vibration. It only monitors the speed of the belt. As long as the belt is turning the alternator and the water pump, the computer is happy. It assumes the tensioner is doing its job. Meanwhile, that harmonic vibration is traveling down the crankshaft, shattering the oil film on the main bearings. Metal is touching metal. The bearings are being ground into paste. But because the temperature hasn't spiked yet, and the average oil pressure is still green, the computer says the truck is healthy. Relying solely on digital diagnostics for a mechanical failure like this is like trying to read Braille while wearing a welding glove. You might feel the general shape of the page, but you are going to miss the story entirely. The screen tells you the engine is running. It doesn't tell you the engine is screaming. By the time the computer finally notices a problem, usually when the main bearing seizes and the crank stops turning, it is too late. The iron is already dead. The digital lie has claimed another victim. So, how do you catch a ghost defect? You put away the tablet. You close the laptop. You stop looking at the data stream that has been sanitized by an algorithm, and you go back to the source. You have to touch the machine. In my toolbox, buried under the digital multimeters and the torque angle gauges, I keep a tool that most young technicians in this shop have never used for its intended purpose. It is a screwdriver with a 24-inch steel shank and a hard plastic handle. I don't use it to turn screws. I use it as a stethoscope. It is the most sensitive diagnostic instrument in this building, and it doesn't require a software subscription. When a truck comes in with this specific complaint, or even before the complaint, when it's just in for a routine service, I perform a test that isn't in the service manual. I start the engine and let it idle. Then, I take that long screwdriver. I press the metal tip against the timing cover, right next to the accessory drive, and I press the handle firmly against the cartilage of my ear. This technique uses bone conduction. It bypasses the air and sends the mechanical vibrations of the engine directly into your skull. It filters out the wind noise of the cooling fan and the combustion clatter of the diesel. It lets you hear the internal organs of the machine. What I hear on these 2024 engines is chilling. On a healthy engine, the accessory drive should sound like a steady hum. It should be a smooth, continuous drone, like a heavy fan. But on these failing units, I hear a chatter. It is a sharp, metallic biting sound. It sounds like a handful of gravel rattling around in a tin can, but much faster. It is a high-frequency buzz that rises and falls in intensity. If you don't have a stethoscope, you can feel it with your bare hand if you know where to touch. I place my palm on the high-pressure hydraulic line coming off the power steering pump. Hydraulic fluid is incompressible. It acts like a solid rod when it is under pressure. It transmits vibration perfectly from the front of the engine block out to the frame rail. When I touch that line on a healthy 2024 truck, I feel a buzz. It feels like holding an electric shaver that is running a little too rough. It feels like a live wire. That sensation is the death rattle of the engine, broadcasting its location through the hydraulic system. The computer is silent. The dashboard is clear. But my hand is vibrating. Here is what is happening physically. The automatic belt tensioner has failed internally. It is no longer damping the pulses from the crankshaft. Instead, it is bouncing. It is oscillating against the belt tension. Every time a cylinder fires, the crankshaft accelerates slightly. The tensioner should absorb that pulse. Instead, it is snapping back. This creates a harmonic vibration. It is effectively a hammer. Imagine taking a small ball-peen hammer and tapping the nose of the crankshaft. Now, imagine doing that 200 times a second. That is what is happening to the metal. This vibration travels straight down the crankshaft snout and into the number one main bearing. A crankshaft bearing relies on a phenomenon called the hydrodynamic wedge. It is a pressurized film of oil that separates the heavy steel crank from the soft bearing shell. The crank is essentially water skiing on oil. It never touches the metal. But this harmonic chatter acts like a jackhammer on that oil film. It shatters the wedge. The vibration spikes the load on the bearing millions of times per hour. It pushes the crank through the oil until steel touches lead. It grinds the bearing surface into a fine paste. The clearance opens up. The oil pressure drops, but only in microseconds that the sensor can't see. Eventually, the heat builds up. The bearing material smears. It welds itself to the crankshaft. And then, at 50,000 miles, the engine seizes. The young technicians look at the seized bearing and say it was a lubrication failure. They blame the oil. But the oil was fine. The oil didn't fail. The physics failed. The engine was beaten to death from the inside out by a vibration that shouldn't have been there. And the moment I felt that buzz in the hydraulic line, I knew exactly what it was. I hadn't felt that specific frequency in a long time. It felt familiar. It felt like history repeating itself. It felt exactly like the problem we solved back in the late 80s, on a machine that these young guys have only seen in museums. The metal was telling me a story I had heard before. To understand why a brand new 2024 truck is eating its own bearings, you have to stop looking at the current service manual. You have to go back in time. You have to go back to 1988. I was working on the assembly line support team back then. The industry was in a panic. We were getting hammered by Japanese competitors who had captured huge market share with superior efficiency, and the suits in the corporate offices were obsessed with a new philosophy called lean production. To close the quality gap while saving money, the mandate came down from the top. cut weight, cut complexity, and above all, cut costs. Every ounce of steel was scrutinized. If a part could be made out of plastic or aluminum, it was changed. If a bolt could be shortened by 3 threads, it was shortened. That was the year the automatic belt tensioner changed. Before 1988, tensioners were over-engineered bricks. They were heavy, ugly steel components with massive springs that could hold up a suspension bridge. They never failed. They utilized lubricated nylon pivot tube bushings and Teflon strips to ensure smooth operation for decades. But they were heavy, and they cost $12 to manufacture. The new design, the modern design, was cast aluminum. It was sleek, light, and it cost $4. On paper, it was perfect. The engineering models said the aluminum housing was strong enough to handle the torque of the engine. And for the most part, it was. But then came the 2-week window. In October of 1988, for a period of exactly 14 days, the foundry that supplied the tensioner housings changed their recipe. They were trying to speed up the cooling process to increase volume. They tweaked the alloy mix, adding a little more silicon and reducing the copper content. It made the casting process faster, and the parts looked exactly the same. They passed the visual inspection. They passed the dimensional check. They bolted onto the engines perfectly. But they had a fatal flaw. The new alloy lacked the necessary fatigue strength coefficient. The original specs called for a T6 temper to handle high cycle fatigue, HCF. But this batch missed the mark. It was brittle at a microscopic level. It couldn't handle the cyclic loading of a diesel engine. 3 months later, the trucks built during those 2 weeks started dying. They didn't snap the belts. They developed that same high-frequency chatter I felt today. The aluminum housing was flexing just enough to set up a harmonic resonance. It destroyed the water pump bearings, the alternator brackets, and yes, the crankshaft bearings. We caught it back then. We didn't have diagnostic computers to lie to us. We had warranty claims and angry fleet managers. We traced the serial numbers, identified the 2-week production run, and issued a recall. We swapped the bad aluminum tensioners for the original spec, and the problem vanished. But here is the critical part. We wrote it down. The lead engineer at the time, a guy who had forgotten more about metallurgy than most modern designers will ever know, updated the blueprint. He added a specific note in the bottom corner of the drawing. It listed the exact chemical composition of the aluminum that failed, and stamped it with a warning. Do not use for tensioner applications due to low cycle fatigue limits. That note is what we call institutional memory. It is the accumulated wisdom of thousands of failures. It is the reason why specs exist. A spec isn't just a number, it is a scar. It represents a lesson learned the hard way. The problem is that institutional memory has a shelf life. It lasts exactly as long as the people who remember the lesson. The engineer who wrote that note retired in 1999. The plant manager who authorized the recall retired in 2005. The physical blueprints, the big blue sheets of paper that smelled like ammonia, were scanned into a server somewhere and then shredded to save space. Over the last decade, the industry has seen a massive brain drain. The old guard left, and they took the unwritten history of the machine with them. The new engineers are brilliant at software and simulation, but they have never held a failed connecting rod in their hands. They look at a part specification and see a cost opportunity. They see that expensive alloy requirement and wonder why we can't use the cheaper, standard automotive grade. They run a computer simulation, and the computer says it will work. So, somewhere in the supply chain for the 2024 model, someone made a decision. They looked at the tensioner specs and decided to optimize the material. They switched to a porous, rapid-cool aluminum alloy to save 50 cents per unit. They didn't know about the 2-week window in 1988. They didn't check the historical archives. They unknowingly resurrected a ghost. They rebuilt the exact same defect that we killed 35 years ago. The only difference is that in 1988, we admitted we were wrong. In 2024, the computer says they are right. I don't trust the cloud. Clouds evaporate. Servers get wiped. Subscriptions expire. I trust paper. In the back of my garage, inside a fireproof filing cabinet that weighs about as much as a small car, I keep the documentation that the industry has thrown away. I have service manuals, technical bulletins, and engineering schematics dating back to the late 70s. When I suspected what was happening with these 2024 engines, I didn't go to the dealership portal. I went to that cabinet. I dug through the hanging folders until I found the file for the 1988 heavy-duty accessory drive assembly. And right there, clipped to the back of a yellowed service advisory, was the original engineering blueprint for the tensioner housing. This is the smoking gun. If you look at the digital spec sheet for the 2024 part, the one the dealership uses, it lists the material simply as cast aluminum alloy. That is a generic term. It is like describing a diamond and a piece of coal as carbon. It is technically true, but it hides the most important detail. The 1988 blueprint is not generic. It is specific. It calls for a specific grade of heavy-duty aluminum, heat-treated to a T6 temper. It mandates a specific casting density to ensure there are no microscopic air pockets in the metal. It specifies high-grade spring steel for the internal mechanism, and crucially, it demands a shot-peened surface finish to resist cracking. Now, look at the 2024 part. I bought one of these replacement tensioners, the same one they are installing in these trucks right now, and I put it side by side with the specs. The new part is lighter. It has a smoother, shinier finish. That isn't a sign of quality, it is a sign of a different manufacturing process. The 1988 part was sand cast and heat treated, a slow process that aligns the grain of the metal for maximum strength. The 2024 part is high-pressure die cast. They shoot molten aluminum into a mold at high speed. It is fast, it is cheap, and it produces a part that looks pretty on the shelf. But inside, the metal is a sponge. This brings us to the physics of the failure. The metric that matters here is something called the fatigue strength coefficient. This isn't about how much weight the part can hold before it breaks in half. It is about how many times the metal can flex before it forgets its original shape. A modern diesel engine is a violent environment. The cylinder pressures in a 2024 engine are nearly double what they were in 1988. Every time a cylinder fires, it sends a torque spike through the crankshaft. That spike hits the belt, and the belt hits the tensioner. The tensioner has to absorb that energy, flex slightly, and then spring back. It does this millions of times. The alloy specified in the 1988 blueprint has a high fatigue strength coefficient, sigma prime F. It can flex and return to zero over and over again without changing its structure. It behaves like a spring. The alloy used in the 2024 part, the cheap die-cast aluminum, has a low fatigue coefficient. It doesn't like to flex. When it gets hit with that torque spike, it doesn't just spring back. It absorbs some of that energy as internal stress. It behaves less like a spring and more like a piece of wire that you bend back and forth until it gets hot. This is the birth defect. The 2024 tensioner lacks the molecular memory to handle the job it was hired to do. It isn't strong enough to dampen the vibration, so it amplifies it. It takes the normal pulse of the engine and turns it into that deadly high-frequency chatter. But the most damning piece of evidence isn't the physics, it is the text on the paper. Down in the bottom right corner of the 1988 blueprint, in the revision block, there is a handwritten note from that engineer I mentioned. It refers to the specific die-cast alloy composition found in the failed batch from that 2-week window. It lists the silicon content and the cooling rate. And then, in all capital letters, it says, "Reject for tensioner arm application. Insufficient damping capacity. Causes harmonic feedback." Read that again. Causes harmonic feedback. 35 years ago, an engineer explicitly forbade the use of this material because he knew it would kill the engine. He wrote it down to protect the future. He left a map to avoid the minefield. And what did the modern factory do? They ignored the map. They saw a cheaper way to make a part, and because the digital system didn't flag the material change as an error, they approved it. They walked right back into the minefield, dragging thousands of fleet owners with them. They aren't just building bad engines, they are defying their own instructions. The blueprint proves that this wasn't an accident. It was a choice to forget. Paperwork is powerful, but in my shop, physical evidence is king. To prove that the factory is lying to itself, I didn't send the failed tensioner back for a warranty claim. If you send a part back, it disappears into a black hole of corporate refurbishment. Instead, I took the seized unit over to the workbench, clamped it in the vise, and fired up the bandsaw. we are going to perform an autopsy. I sliced the tensioner arm right down the center line, exposing the cross-section of the aluminum casting. Then, I took a slice of the 2024 metal and placed it under a stereo microscope. A research lab would use a scanning electron microscope, SEM, to see this at 50,000 times magnification, but the defect is so gross you can see it with a standard lens. The difference is visible to the naked eye, but under the microscope, it is a crime scene. The vintage part looks uniform. The grain structure is tight, dense, and interlocking. It looks like a solid block of gray slate. That is what happens when you heat-treat aluminum properly. The molecules align to support each other. But when I looked at the 2024 part, the metal looked like a sponge. It was full of what we call microporosity. Because this part was die-cast at high speed to save money, air got trapped inside the molten metal. As it cooled too quickly, that air formed microscopic bubbles. Under the lens, the metal looks like a honeycomb or a sugary confection. To a bean counter, that is just a lighter part. To an engineer, those bubbles are stress concentrators. When the tensioner arm flexes under the torque of the engine, the stress doesn't flow through the metal like water through a pipe. It hits those air pockets and piles up at the edges. This creates what metallurgists call crack initiation sites. I zoomed in on the fracture point where the arm had started to twist. You could see the slip bands. These are microscopic lines that appear on the surface of the crystals within the metal. Think of them as stretch marks for iron. They appear when the metal has been pushed past its yield strength in a high cycle fatigue, HCF, scenario, tens of millions of load cycles. These slip bands were clustered around the grain boundaries, specifically radiating out from those tiny air pockets. The metal was screaming. It was trying to hold the tension, but the porous structure gave it nowhere to transfer the load. The slip bands turned into micro cracks, and those micro cracks joined together to form a fracture that was invisible from the outside, but fatal on the inside. This structural weakness is what allowed the arm to bounce, creating that harmonic chatter that destroyed the engine's main bearings. But the autopsy didn't stop at the casting. I also pressed out the pulley bearing, the one the manufacturer stamps with lifetime lubricated. Lifetime is a marketing term, not an engineering promise. It assumes a specific operating environment. It assumes the bearing will spin smoothly. It does not account for a high-frequency hammer effect. When I popped the seal off that bearing, there was no grease left. It was bone dry. Instead of smooth synthetic lubricant, the race was filled with a fine, red powder. That is the hallmark of fretting corrosion. Here is what happened. The vibration from the weak casting was so intense that it literally shook the oil molecules out of the thickener in the grease. The lubricant separated, the oil leaked out past the seals, and the thickener turned to dust. The ball bearings were then running steel on steel, grinding themselves down every time the engine fired. The heat generated by this friction didn't show up on the coolant temp sensor. It was localized. It cooked the bearing race, causing it to drag. That drag added resistance to the belt system, which put more load on the tensioner arm, which caused more flexing, which opened up more cracks in the porous aluminum. It was a self-feeding cycle of destruction. The diagnostic tablet saw none of this. It saw a belt speed that was within tolerance. But under the microscope, the truth is undeniable. The slip bands, the porosity, the red dust, they are the forensic record of a birth defect. The metal kept a perfect log of the failure, starting from the very first mile. The factory can deny the flaw in the boardroom, but they cannot argue with the grain structure on the workbench. The metal doesn't know how to lie. The official quote from the dealership to get this truck back on the road is $22,000. That covers the long block, the labor, the fluids, and the downtime. They want to replace the victim. I want to remove the killer. The actual fix, the one that solves the physics problem, costs less than a lunch break. I don't use the factory replacement part. I order a severe duty tensioner from a legacy aftermarket supplier. These are the guys who didn't throw away the 1988 blueprints. Their part is heavy. It is made of dense, heat-treated alloy. It doesn't look as pretty as the factory die-cast unit, but it doesn't flex. But the hardware is only half the battle. The real secret is a stainless steel shim. It is a simple washer that costs exactly 5 cents. You see, because the engine block was machined to accept the flexing, porous aluminum part, the mounting boss is often milled at a slight deviation. It relies on the cheap part bending to fit. When you install a rigid, proper tensioner, It needs to be perfectly square to the crankshaft. So, I slide that 5-cent shim behind the lower mounting bolt. It corrects the geometry by a fraction of a degree. It restores the alignment that the assembly line robots missed. It ensures that the belt runs true, without the side load that excites the harmonic vibration. Think about the absurdity of this. The corporate system is designed to burn $20,000 of the customer's money because they cannot conceive of a 5-cent solution. They are trapped in a rigid protocol that forbids modification. To them, adding a shim is unauthorized tampering. To me, it is engineering. The parts changer trusts the part number on the box. The mechanic trusts the geometry of the assembly. When I torque that bolt down and turn the key, the result is immediate. You don't need a sensor to tell you it's fixed. The silence is deafening. The chatter is gone. I put my hand on the hydraulic line, the one that was buzzing like a live wire, and it is dead calm. The engine settles into a deep, rhythmic idle. The harmonic hammer has stopped swinging. The hydrodynamic wedge on the main bearings is intact. By spending $80 on a better part and 5 cents on a shim, we have just saved this truck from the scrap heap. This situation is a warning. It is a testament to the high cost of forgetting. We have built an entire industrial ecosystem that values the speed of the assembly line over the wisdom of the blueprint. We have traded deep institutional memory for superficial digital convenience. We assume that because a machine is new, it must be better. But as we just proved, new often just means cheap. As long as the factories continue to ignore their own history, these ghost defects will keep haunting the modern fleet. You cannot code your way out of a metallurgical problem. You cannot fix a bad casting with a software update. And you certainly cannot diagnose a physical failure if you are only looking at a digital screen. My advice to you is simple. Don't throw away the old manuals. Don't trust the lifetime rating on the box. When the dealership tells you a machine is dead, but the codes are clear, don't walk away. Put your hand on the iron. Listen to the rhythm. Find the guy who retired 5 years ago and ask him what he remembers about the alloy changes in the 80s. We have to stop being operators and start being mechanics again. We have to respect the laws of physics because they are the only laws that cannot be rewritten by a corporate memo. The diagnostic tool is just a suggestion. It is a best guess from a blind machine. But the vibration, the heat, the grain structure, that is the truth. The computer is guessing, but the metal knows.